Hello there. Okay, so let's talk today a little bit about confidence intervals. Uh-oh, lost my little cheat sheet. Well, so let's talk really quickly about why do we create a 1 minus alpha confidence interval. All right. So when I say a 99% confidence interval, or a 95% confidence interval, or an 80% confidence interval, how do we find the critical z values? And what do we mean by alpha over 2? And what is alpha? And why? What is all of this notation? All right, so let's kind of back up. All right, so here you can see in my little diagram, here's a sketch of the normal distribution curve. All right, right in the middle of our distribution, there is where our mean should be. Okay, right, so remember that's 0 though on the normal distribution. And what we're looking for is we're looking for our confidence interval to contain, well, we want it to be, for example, let's say a 95% confidence interval. So that means we want this area in the middle to be 95%, so that 95% of the time we're containing the true population mean. Okay. Sometimes, 2.5% of the time our population mean might be beyond, it might be bigger than what we say the upper limit is, or 2.5% of the time it might be smaller. So that sum total of 5% of the time, the true mean may not be in our confidence interval. But the rationale behind saying why it's 1 minus alpha instead of just saying the percentage is to help us find that z value, that critical z value that we're going to need to find. All right, so that we can find the critical plus or minus z subscript alpha over 2 values so that we don't have to just memorize them. There are quite a few that we will be able to memorize. So you don't have to memorize them, but sometimes you may get to. You don't have to always look them up, but basically here, instead of saying, just 0.95 and there you go, that's it, that is not really connected to the area underneath the curve. And so that's why we've set it up as 1 minus alpha. So what we're going to be doing in this example, this is our favorite one, by the way, in case you didn't know. You have a favorite example of finding a critical z subscript alpha over 2 value. All right, this is the 95% confidence interval. All right, so what we're going to do is sketch our distribution curve, and you can see here I put 95% or 0.95 in green here, shaded in the left tail over here and the right tail over here. And so, like I was mentioning in the above graph, the interior of this contains 95% of the area. The other 5% of the area is distributed equally, 2.5% above and 2.5% below. So that sum total adds up to 1.00 or 100%. So, do we get this instantaneously? No, we don't. We actually get this by setting 0.95, whatever our desired confidence level is, equal to 1 minus alpha. So that is our percent divided by 100%, so 95% divided by 100%. That's how we got that 0.95, all right? We're going to set that equal to 1 minus alpha. Right here, I did the algebra I did it sloppy. If you follow these steps, they're not really logical. I'm reading them and I'm like, who did these? Anyhow, what I would maybe do is well, think of it this way. Let's take 1 and subtract away our desired level of confidence. Okay? And whatever is left over, that is actually alpha. So here, alpha, the significance of alpha is that leftover 5% of the time that we're not going to get it right, that our data is not a sufficient estimator for the actual true population parameter. So anyhow, what I've done here is I've taken 1 minus alpha, set it equal to 0.95, going through by hook or by crook, some way or another. I get out alpha equals 0.05. If your algebra looked a little bit nicer, kudos. Mine, I don't know why. Then what that means is we take 0.05 and we divide by 2. So do we have to solve this for alpha over 2? Well, yes and no. Yes, we do. Let's just leave it at that. Sorry, it's not yes and no. It's just yes. Yes, we do. Solve it for that. Okay. Then coming back up to the diagram here, we'll label this as 0.025. We'll label this as 0.025. So, like I said, it's not automatic that we know boom, 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 right? We can figure it out intuitively. We can figure out, geometrically speaking, right? But here's the algebra. So that is basically the rationale behind this. Okay, and then how do we get these critical z values? Well, this is basically a reverse lookup. If we focus in, ignore that one, ignore the right-hand side of this graph, just look at the left tail, and you can see we want the left area beyond whatever this z value is. I'm calling it negative z subscript 0.025, and over here we have positive z subscript 0.025, because remember, alpha divided by 2 is 0.025. Generally, I just say the critical z value, or maybe z subscript alpha over 2. All right, so what we were doing here is I am going to find my left area table 250 exactly, or as close as I can get to it. There it is exactly. And what I showed you here is, where is that? It's in the 0.06 column, and it's on the negative side, so it's in the negative 1.9 row. So this value would be negative 1.96. This value would be positive 1.96. So here, plus or minus z subscript alpha over 2 is how I would just say it. Or you could say it as z subscript 0.025. But either way, that is equal to plus or minus 1.96. So remember, this is our favorite one. Didn't know you had a favorite confidence level interval, confidence interval to create. Yeah, but we do, yay. Yeah, so that is just a little bit of background about why we use this notation, right? What is the connection between our confidence level and how we go about finding the critical z values for that confidence interval. All right, so let's stop there.